Welcome to Lecture 10 for Chemistry 141. We're going to
Now, when we have more than one sublevel within an n level, so we have different values for L, previously what we did is we calculated a single energy for a single n level. So we looked at what's the energy of the n equals 1, what's the energy for the n equals 2, what's the energy for n equals 3, etc. But as it turns out, what we end up with is that the different sublevels or the different subshells, so S, P, D, and F, etc., they actually have different energies within the same level. And the order that they go in is that the lowest of those energies is the s orbital, the next lowest is the p orbital, the next lowest is the d, and the next lowest is the f. So within a given n level, the s is always the lowest, the p is next lowest, the d is next lowest, and the f is the highest of those four. The overall energy that we were calculating for that n level is actually a weighted average of all of those different sublevels. Now, any orbitals within the same sublevel have the same energy. What that means is that even though the s is higher than the p, all of the p orbitals have this exact same energy. All of the d orbitals within a subshell have the same energy. So we call these degenerate orbitals. In chemistry terms, when we say energy is degenerate, it means that it has the same energy. So as an example, the px, the py, and the pz, three different orbitals with an L equal to 1, they all have the exact same energy. Now, why does this splitting happen? Well, it occurs as a result of penetration and shielding. So we can look at how energy of the orbitals interacts with the nucleus. And the closer an electron within an orbital is to the nucleus, the lower its energy, because the stronger attraction it's going to have to the positive charge in the nucleus, given that the electron is negative. And this just follows Coulomb's law. Okay, the more attraction that is felt, the more stable something is, and the lower the energy is. Now, as far as penetration, what that means is if we look at these different nodes that we saw in the previous lecture, we see that the 1s here is closest to the nucleus, has the highest density closest to the nucleus, so it's going to be lowest in energy. But why does the 2p have a higher energy than the 2s? Well, it has to do with the penetration of the 2s. Even though we see that the maximum radial probability for the 2s is farther away than the 2p here, we also see that the 2s has that little node in here, has that small maximum here very close to the nucleus before it has the node down here. This penetration into the 1s region here of the 2s gives that 2s orbital some electron density close to the nucleus, which lowers its energy. So as a result, the 2s orbital has a lower energy than the 2p. We can expand that also to the n equals 3 orbitals, and again we see that the 3s maximum is farther out than the 3p, which is farther out than the 3d. However, because of penetration, the order of energy is actually the 3s is lower than the 3p, lower than the 3d. The 3s has two areas of penetration here that bring its electrons closer to the nucleus, and the 3p has this one area of penetration that's closer than the maximum of the orbital itself. And so that penetration, that small probability of finding electrons close to the nucleus, lowers the energy of the 3s below the 3p and the 3p below the 3d. It's a weird concept. So let's look at the concepts of penetration and shielding a little bit more. So for penetration, what this means is that the radial distribution of electron for these higher energy orbitals shows some electron density close to the nucleus. And again, this is because of all of those different nodes. That sine wave that governs the radial probability gives us some density really close to the nucleus, even though the maximum is far away. So what this does is lowers the energy of that orbital more than expected. And what shielding means is shielding is like a screening of the outer electrons by inner electron clouds. And so something that's farther away from the nucleus doesn't really feel the full power of the nucleus because you can think of it as being blocked by those inner electrons, and so they don't feel the full nuclear charge. And we end up looking at something that's called Z effective. And Z, of course, remember, is the total number of protons within the nucleus. And an outer electron may not feel all of that positive charge because it's being blocked by those inner electrons. We'll discuss Z effective later in the chapter. What all this leads to is a different filling order than we would expect as far as how orbitals fill in with electrons. We can't just say, well, the 1s goes, and then the 2s and the 2p, and then the 3s, 3p, 3d, and then the 4s, 4p, 4d, 4f, etc. So, and the reason for this is because of the effects of penetration and shielding, the outer sublevels, such as Ds and Fs, to some extent Ps, go up in energy higher than the average N level, and the inner sublevels, such as Ns and sometimes Ps, go down in energy. And what this causes is we get areas of overlap between the N levels. So we may have, well, what we'll see here in a moment is that we actually have a 4 subshell. So the 4s subshell is lower in energy than the 3p. So let's take a look and see how electrons fill in. And they fill in according to energy. Here we go. So our very bottom orbital here is our 1s, lowest in energy. And then we have our 2s, then our 2p's. Change my colors here. And then we've got our 3s, so everything is going in order here. Our 3p's are the next lowest in energy. But then the next lowest energy here is the 4s. We see that the 4s is lower than the 4p's and the 4d's. And once the 4s is filled, then the next lowest energy is in fact the 3d's, followed by the 4p's, followed by the 5s, followed by the 4d's. So things start filling in an order different than what you would expect. We'll learn some tricks as we go along to show how we can use the periodic table to help us fill in these energy levels.
And what the Aufbau principle is really looking at is building up of the electrons in the orbitals in an atom. And essentially what this means is that when we're putting our electrons into the orbitals of an atom, we can't just put them in any order, and we can't just put any number of electrons that we want into a particular orbital. As it turns out, electrons will always go into the lowest energy orbital available, and each orbital can only hold a certain number of electrons. And so it's something we always have to keep in mind when we're adding our electrons into an atom. Now, when electrons are in their lowest possible energy arrangement, this is what we call a ground state. And what this means is that there's no empty locations in a lower energy than we have electrons placed in the atom. And so again, we call this a ground state. If we have electrons in a higher energy than what's available, then we call that an excited state. So Hund's rule deals with filling in degenerate orbitals. So anytime we have P subshell or a D subshell where we have multiple orbitals at the same energy, Hund's rule states that electrons will go in as singles with parallel spins before they begin to pair up. And the reason for this is that there is a repulsive interaction between electrons that are in the same orbital, And anytime you have a repulsive interaction, the energy of the atom is going to go up, and Mother Nature always wants to have energy as low as possible. So this is why they go in as singles. So if we look at carbon here, it has the electron configuration of 1s2, 2s2, 2p2, and this is because carbon has 6 electrons, and the 1s fills in first, and then the 2s, and then if we have any left, they go into the 2p there. And so we see that we've got our 1s filled, our 2s filled, and then in the 2p, we take those 2 electrons and put them in as parallel spins, meaning that they are both either spin up or both spin down. It's kind of convention to use the spin up first. And notice that we've got these 2 electrons here in 2 separate orbital locations. And if we had an additional electron for the next atom, then we would put it here before we begin to pair up. So just kind of a brief summary of how we're filling in these things, because we do quite a few electron configurations as we go. Electrons always fill in order of lowest energy, and if we look at the order of electron filling, it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc. It seems like an awful lot to have to try to memorize. We'll learn a trick at the end of today's lecture that shows a little bit different way of doing that. So another part of the summary is an orbital itself can hold no more than 2 electrons, so 1 spin up and 1 spin down, and that means that each subshell can hold, for an s subshell with 1 orbital, it can hold 2 electrons. P orbital, or P subshell rather, has 3 orbitals, and it can hold 6 electrons. Your D subshell has 5 orbitals, and that can hold 10 electrons. An F subshell has 7 orbitals, and that can hold 14 electrons. Now for each of these, the number of orbitals contained in each of these subshells is equal to the number of m sub L values present in that particular that subshell. And then the last part is when degenerate orbitals are filling, electrons will occupy orbitals singly with parallel spins before pairing up with opposite spins. So just as a couple of examples here, we've got beryllium and boron. There we see beryllium with 4 electrons, so we go 1s2 and 2s2. So we then have our orbital diagram there. With boron, 5 electrons. We fill the 1s, fill the 2s. We've got that 1 electron going into the 2p. We saw carbon already earlier in the slides, so we'll skip that one and go to nitrogen with 7 electrons. And there we see those 7 electrons there, and we've got all 3 in the 2p there as singles and parallel spins, all spin up. And then we've got oxygen with 8 electrons. Well, now that we've added 1 more electron, we now need to pair up that very last electron that goes in, and it pairs up here with an opposite spin from the first one, and now we've only got 2 unpaired electrons. Let's try a couple electron configurations, and the first one we've got is aluminum, and aluminum, when we look on the periodic table, has 13 electrons, so we're going to write that one in as 1s2, 2s2, that's 4 electrons, 2p6, that's 10 electrons, 3s2, it's 12 electrons, and 3p1. So that would be our electron configuration there for aluminum. For phosphorus, phosphorus has 15 electrons, and so we're going to have something very similar. We're going to have 1s2, 2s2, 2p6, 3s2. So now that's got me 12 electrons, and for 15 I can go 3p3. And if we were to do the orbital diagram there for the phosphorus, our 3p would have those 3 orbitals, and we would have 3 parallel spins just like that. Now, another way of expressing an electron configuration is through something called noble gas notation. So let's take a look at one of our last examples, aluminum. And if we look at the electron configuration, we see it's 1s2, 2s2, 2p6, 3s2, 3p1. Not a particularly large example there, but if we were doing something really large, something like lead or bismuth down in the 80s, our electron configuration would be significantly bigger. And so for those types of elements, a different notation was created called the noble gas notation. And we see here that the first part of the configuration, the 1s2, 2s2, 2p6 portion, is exactly the same as neon. And so what we can do when we're doing our electron configuration is we have our 1s2, 2s2, 2p6 here in our aluminum configuration, and we just replace that with neon. So we put that neon in brackets and then fill in what's left, which is a 3s2, 3p1. And so what this does is it tells us the number of electrons that we consider to be valence electrons. Let's talk a little bit more about valence electrons. So valence electrons are what we have in our last valence shell, or our last n level as we're filling in. So as we move across a period, filling in electrons, they all go into that same n level until we move down to the next period. When we move to the next period, well, now we've got a whole new outer layer, and we've got the next highest n level in our electron configuration. So the number of electrons that we have in the highest n level we call valence electrons. And these are the most important electrons that we have on an atom, because these are what do the chemistry, they get involved in the bonding, and they're the ones that we worry about most often. So it's valence electrons. Any other electrons that we have in the atom are called core electrons. So these are electrons in lower energy filled shells, and they're much closer to the nucleus. They're held very tightly by the nucleus, and they don't really get involved in any chemistry. So we really only concern ourselves with the valence electrons. So if we look at something like silicon here, we've got our core electrons here on the inner ones, so the n equals 1 and the n equals 2 shells, and then our valence electrons are in the outermost shell, so we've got 3s2, 3p2, and so we've actually got 4 valence electrons there in silicon. Let's take a look at germanium. Let's write the electron configuration for germanium. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. If we look at the number of valence and core electrons, we see something we may not necessarily expect, but we've got our core electrons here. We've got 28 of them. Notice that we include the 3d10 as part of our core electrons. And the reason we do that is because it has an n equal to 3. When we're looking at our valence electrons, we look at the highest n level. The highest n level here is n equal to 4, and so that's why only these guys here are my valence electrons. So I've got 2 in the 4s, 2 in the 4p, so germanium here has only 4 valence electrons. Now we can also use the periodic table to help us write electron configurations, and it becomes a very important tool when we're doing so. The last electron to fill in can be found by finding where the element lies in the periodic table. And what we mean by where it lies is what block is it in, and then which element is it in that particular block. We've got different blocks that we'll see here in a moment, but we've got S blocks, and they go as NS when we're filling in our electron configuration, where N is the period. We have P blocks, D blocks, they fill in as n-1, and F blocks, which fill in as n-2. Let's see what all that means. So here we have a periodic table. And if we look at our S blocks, we see them here in blue. So when we're in an S block, we're filling in S electrons. And what we see entered here on a periodic table, this is the last entry that we would have in an electron configuration. And we see that they're all S's. If we look at the P block here, this is our P block right here, over here. Notice that we've got 6 different columns for a P block, and there's 6 electrons that can go into the P subshell. We've got 2 groups, 2 columns for the S block, and the S subshell can hold 2 electrons. Now we've got our D block here, and our D block is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 wide, and a D subshell can hold 10 electrons. So this is not by coincidence. And our F's, of course, then can hold 14. But if we look at how things fill in, as we're going across the periodic table, we fill in our S blocks as we go. So we would fill in, let's say we want to look at something like fluorine here, which is way over here. We would go across, we go 1s, 2, that finishes out the 2's, or the S's there. We jump down to the next period, and our S's go as the N period goes, so that as the N level goes. So in period 2, we're going to have 2s2, and then we go 2p, 1, 2, 3, 4, 5 to get to fluorine. And so we can use the periodic table not only to tell us the last entry in an electron configuration, but we can figure out everything as that we have going on in an electron configuration by reading left to right, top to bottom, looking at the periods. We mentioned that things like the D block go as n-1, and notice that when we're in period 4, we're actually filling in the 3D. When we're in n equals 5, or the 5 period, we're filling in the 4D. The F block was n-2, and we see that the lanthanides actually start right there. And so as we start to fill in our F blocks, even though we're in period 6, we see that the F block is actually a 4F. Let's take a look at some examples here. And so if we're looking at chlorine, we can do a couple of different things. We can use noble gas notation, and here we see for noble gas notation we find our previous noble gas, not the closest noble gas, but the previous noble gas. Okay, so we could say neon, so let's just write neon here, and then we have what's left. We've got 3s2, and then we come across and we've got 3p5 to get to chlorine. Okay, so our electron configuration would be neon, 3s2, 3p5. Or if we wanted to go all the way across, we would have 1s2, 2s2, 2p6, 3s2, 3p5. Look at another example here, selenium. If we go with our noble gas notation, we've got argon here. So let's just put that in our brackets here. So we have argon. And then as we come down here, we've got 4s2. We come across here and we've got 3d10. And then we've got 4p4. So we look at the period number, the block number, and which element we have in that block. Okay, so lots of different ways of writing electron configurations. Easiest way to get used to doing them is lots of practice. Well, that finishes out Lecture 10. I hope you found the lecture capture useful, and if you got any questions, give us a call.